Okay?
Yeah, makes sense.
And then what we did is that we then used the fact, that, so if we now take the group, say SON, and then we say, okay, let's take a small element, so G of delta alpha, and this has the form of 1 plus alpha dot x, or as I was writing before, alpha I x I. And now, we know that for orthogonal groups, G transpose of G is 1. And they're real. So now what we can do is that we can, insert this into the left-hand side, and then 1 transpose is just 1, right? Alpha I are numbers, so we don't have to worry about transposing them. Xi has to get transposed. And the second factor, nothing is transposed. So if we are going to be nitpicky, we are going to use a different index here, because they are dummy indices, right? I don't know if you saw the tutorial I posted yesterday, Moon posted yesterday, but it explained dummy indices and stuff like that. So now if I expand both sides, well, this side, the right side, nothing to expand. So we expand and keep to order alpha. Then the left-hand side, I have 1, and then I have alpha I, xi transpose plus x of I, and then order alpha squared term. And we are going to ignore that. So then, this cancels out. This we don't need. And alpha i's are arbitrary. They're small but arbitrary. So I should probably have written delta here. Delta, delta, and delta. So then this tells us that for orthogonal matrices, for the orthogonal group, the generators are antisymmetric. Okay? So for SON, the generators are antisymmetric. Okay? And then we can say, okay, what other property of the generator we can derive? The other property is that the determinant of G is 1, right? For the continuous transformations. So that means the determinant of e to the power alpha I xi is 1. But we know that the determinant of e to the power alpha I xi is e to the power trace of alpha I xi equals to 1. But these are just numbers, so they just come out of the trace, and trace is linear. So we can write this as trace of xi equal to 1. So now, the argument of the exponent is just a number. And these are arbitrary. So for this to be true, the trace of each generator has to be 0. So hence, we decide that the SON generators are antisymmetric and traceless. Okay, so if, as physicists do, I want to represent an element of SON as e to the power I theta or I alpha dot xi, in that case, alpha I is still real, then xi is not just antisymmetric, it's actually pure imaginary, and therefore it's Hermitian. But that's like a thing that physicists do, and and because I'm a physicist, I will switch between these two conventions. So for SO3, if I write the algebra of the generators, it's basically this thing. This is the mathematician's SO3 algebra, but physicists define their generators to be I times xi. So for physicists, the SO3 algebra, which is the angular momentum algebra, becomes this. Okay, so I think this probably gets, kind of answer some of Saif's questions. Saif, did you want me to go and also explain how the closure of the closure property of Lie group leads to the general form of the Lie algebra?
No, I think I got that one.
Okay.
Is there supposed to be a 2 in any of these?
No. So the idea is that the Pauli matrices, they satisfy this algebra. And usually for SU2, what we do is that the SU2 algebra is the same as this algebra, as SO3. Okay, so then for SU2, what we define is that we define it to be, sorry. And when you express this algebra in terms of the taus, so there's an I here, I forgot. So that factor of 2 goes away. Okay?
Yeah, makes sense.
Okay. Okay. So shall we move to what Rahul was asking about?
Sir, I had a question regarding this, is that you commented that imposing these tracelessness property and that of the anti-symmetry, we can necessarily conclude that in the 2 times 2 case, this will give rise to the Pauli matrices. Could you shed some light on that? Or
right. So if you have, say, in 2 dimensions, so in 2 dimensions, say X is a 2 by 2 Hermitian traceless matrix, okay? So if X is 2 by 2, I can write X as A, B, C, D. That means there are 1, 2, 3, 4, 8 real parameters, right? So, but we say that it's Hermitian, so X dagger has to be equal to X. Right, so that means that we have A star, C star, B star, D is A, B, C.
So D star,
D star, A, B, C, D, right? So this, cuts down the number of independent parameters from 8 to 4, right? Because how many? So we have, okay, so here we say, so this means that A needs to be real, right? Saying that A is real. So this is, and then it also says that D is real. Sorry. Okay, so we have 2 parameters, A and D are 2 real parameters. But we also have another equation, which is B is equals to C star, right? Here, there are two equations, right? Taking the real and the imaginary part. So of the 4 parameters here, we have 2 left. So this equation cuts down 2 more parameters, right? 2 more real parameters. So this equation tells us that the number of parameters so far is 4. But then we have to take into account that it's traceless. So if I say it's traceless, so trace of X is 0. So that means A plus D is 0. And therefore, D is minus A, right? So, so then we have our matrix must be 1, A minus A. And here we have, say, if I write, say, let me go back. Let's write B in terms of 2 real things. B say, I don't know, E plus I of F, right? So let's write E plus I of F, but this must be the complex conjugate of this thing. So here we have E minus I of F. So this is the most general permission traceless matrix. And this we can write as E sigma 1. Let's put a minus sign here just for, sorry. Let's call it E minus IF and call this E plus of IF. Then this is E sigma 1, F sigma 2 plus A sigma 3. Okay. Does it answer your question, Nahi?
Yes, sir.